All right, in this video, we're going to go over precipitation hardening again, but now using what we know about phase diagrams. All right, so precipitation hardening, that practice we use to form these secondary particles that impede dislocation motion, is done in 3 stages. So this actually seems like more than maybe what's necessary, but hopefully you'll see why we do each step. So the first step is what's called a solution heat treatment. So basically what we do is we heat up the alloy above the solvus to yield 100% of the primary phase, or in this case, alpha. So basically we heat it up to this point here, which is T0. And this is in a region where only alpha is present. So this is the solvus, as you remember. So we're heating it above so that we have increased solubility and everything will be in the alpha phase. So that's the first step. The second step is not to actually go straight to forming precipitates. The second step is actually to quench. So we rapidly cool to T1. And what this does is it retains that alpha solid solution. So we basically quench the structure that we have at T naught at T1. And that's done for a very specific purpose, and we'll talk about that in a second. And finally, 3 is the actual precipitation heat treatment. And so that's where we heat back up to some intermediate temperature up here, and then we nucleate and grow those small particles of beta in this case, which is the other phase over here. So the whole kind of procedure here, if we plot it in time versus temperature, looks like this. We heat it up to that solution treatment, hold for some amount of time to get 100% alpha. We quench it, so very rapidly cool, and then we bring it back up to some intermediate temperature. And so this way of doing it with this quench and then the precipitation treatment is done so that we have more control over the precipitation treatment. If we, as opposed to doing the quench, if we directly cool to T2 to do the precipitation, we have less control because during that cooling, we could get precipitation. And so this allows us to control it at what temperature that we want as we bring it back up in temperature. So it allows for a little bit more control. And also, once we heat it back up, there's a greater driving force for those particles to form. All right, so we're going to talk about the aluminum copper system because this is a common one for precipitation hardening. So in this case, we have alpha, and then we have theta over here. And you'll notice that's not the complete diagram again. So this is an intermediate phase. But this is our precipitation hardening phase, theta. And this is what we're going to sort of try to grow. So those are the precipitates. And so there are also, however, there are also other intermediates that form sort of non-equilibrium phases that can form in the process. So let's kind of look and see what it might look like. So this kind of shows what this looks like when we're in the pure alpha region, right? So we have aluminum, and then we have a small amount of copper, and it's all distributed evenly and randomly throughout the lattice. So it's a solid solution. When we start to form particles, those copper particles tend to migrate to a central location and form an intermediate phase. And so this one, which you can kind of see looks like it's roughly 50% each of those, is called theta double prime. And this is kind of an intermediate. It's not theta, but it's very close to that structure. So you can see it's kind of very small. So we're only talking, a few atoms here in these small particles. And then eventually we'll get to theta particles, which you can see here. they're kind of trying to show that there's a lot of strain in this lattice because the particles are so small. Whereas here, there's less of that strain happening, but we still have a unique phase here as theta. So there's actually quite a bit going on when we do this precipitation hardening, because in this case, we don't have just the equilibrium phase, which is theta. We actually have the double prime, which we just showed, and we also have a single prime as well. So there's actually a lot of different phases happening, as well as what we call zones, which is something that's not quite a phase yet. And so this plot basically shows us, if we look at the aging time, the precipitation aging time versus strength, it actually shows us that we get a maximum strength here, where we actually have a mixture of the two metastable phases, double prime and single prime. So even though the phase diagram, if we go back here, says theta, we can often have these intermediate or metastable phases, and those are the ones, since they're so strained, like it's shown here, actually increase the strength. They're smaller and then they're strained. So those two effects increase the strength of the overall alloy. So that's what we see here. We see initial strengthening with the zones, and then continues to strengthen with the theta double prime. But then as we start to get more and more of that single prime, it's what we call overaging, which means that the strength is going back down. So if we reach the equilibrium phase, we've actually gone too far in this system to achieve maximum hardness. And so that's what we have with overaging. All right, so this looks at a series of different times and temperatures for these various treatments, and we're going to look at yield strength and we're going to look at ductility. So the same kind of trends that we see with strength and ductility hold, because if you increase strength, you tend to decrease ductility. But what this also shows is that if we increase temperature, we decrease the strength. You can kind of see that here. So 121 Celsius as an aging temperature has the max yield strength, and then it kind of goes down here. However, you can see that 121, it's somewhere between a month and a year for which that treatment takes. And then it's a day for 149, and then 1 hour for the 204, and then 1 minute for 260. So you can see that with something like a minute, it's very hard to control that to any great degree. So there's a balance of, you don't want the thing to take a year, but 1 minute types of treatments are really hard to control with temperature. So that's kind of the trend that you see with this, but they all have a maximum hardness or maximum yield strength, and then they decrease as they overage. And the same with the ductility. But in this case, you see more of a minimum in those cases. But the same trend is shown. So for the 121, it takes a day to reach the max ductility, but then it decreases. And the same thing an hour for the 141. And so you see that the ductility decreases with these treatments. The ductility will kind of increase. Sorry. The ductility will decrease as we do this. But again, it's happening at the reverse. So if we look at this 121, for example, it never really fully reaches, but the max, the lower, the minimum here, which is 12 or so, is at that time frame in between a month and a year, right? And then for the 149, we see that this happens between a day and a month. It has kind of that minimum here, and that corresponds with the maximum here. So we decrease ductility as we increase the strength. That trend stays the same as well.